Alright, so for today's video lesson, we're going to cover topic 16.2. This is radioactive decay. So Ernest Rutherford and his colleagues discovered when elements undergo radioactive decay, they are transformed into other elements. So this process is known as transmutation, and transmutation is when elements undergo radioactive decay and they turn into other elements. Okay? Transmutation occurs because elements are identified based on the number of protons they contain. Remember, this is the atomic number, and this will define number of protons it contains, so that is our atomic number. Okay, and if the atomic number changes, the number of protons will also change, and therefore we will have a different element, right? Isotopes are elements which have the same amount of protons, but a different number of neutrons. Okay, so if we have a different number of protons, we have a different element. So we have three different types of decay that we're going to focus on. So the first is alpha decay. We learned about alpha decay a little bit yesterday. This is when we have a loss of a helium nucleus. Okay, that is 2 protons and 2 neutrons. Okay, so in alpha decay, there's a loss of 2 protons with 2 neutrons. So this is an alpha particle or a helium nucleus. And this right here is an example of an alpha decay equation, right? We have a sample of uranium. It is losing a alpha particle or a helium nucleus. Okay, and then that becomes thorium. So if we look at our mass number, we have 234 plus 4 equals 238, so we're balanced for our mass number. And for our atomic number, we have 92 going in and 90 plus 2 going out, so that is good. Remember, when we are predicting these types of nuclear decay, or even when we're doing beta and gamma decay, it is important, it's essential that everything is balanced. Okay? So again, alpha decay is the loss of a helium nucleus. Okay, so we want to write the alpha decay equations for each of the following. So the first one is thorium 230. So thorium has 90 protons. Thorium will always have 90 protons, right? And in this case, thorium 230 indicates the mass number, okay? So thorium is TH, and it is undergoing alpha decay. So we're losing a helium nucleus. And if thorium loses 2 protons and 2 neutrons, it will turn into radium, which is 88, radium 226. Okay, and again, we need to make sure that we have balanced mass and atomic numbers, which we do here, so we are good. Okay, uranium 238 is undergoing alpha decay. So uranium has 92 protons. It has a mass number of 238. Uranium is just U. Okay, and this decomposes. It loses an alpha particle or a helium nucleus. And if we lose 2 protons and 2 neutrons, we now have thorium 234. Okay, and again, it's important that we make sure that we have balanced reactants and products. Okay, last one, polonium 214. So again, I would encourage you guys to try this one on your own, and it starts with locating polonium. Polonium has 80 protons. and we know that it has 214 protons and neutrons. And this decays via alpha decay. So we have a helium nucleus coming off. And if polonium-214 loses 2 protons and 2 neutrons, it becomes lead-210. Okay? Now, you guys are going to come across the terms parent nucleus and daughter nucleus. So the parent nucleus is what we have before the decay, and then the daughter nucleus is going to be what we have after the decay. Okay, so I'm just going to head and identify my parent nucleus, or my parent nuclei. Okay, and then our daughter nuclei in these questions is not going to be the alpha particle, but it is going to be the other element, okay? So thorium will be my daughter nuclei in example 2, and lead will be my daughter nuclei in example 3. All right? So that is alpha decay. And as we just mentioned, so during any process of radioactive decay, the name given to the original nucleus is the parent nucleus, and the nucleus that remains, which is not the alpha particle / the helium nucleus, is called the daughter nucleus, which we just identified on the last page. Okay? Okay, so second type of decay is beta decay. Now, beta decay, we have 2 different forms of beta decay. There are beta negative and beta positive. Okay, so for beta negative decay, there is an increase in the number of protons as a neutron is changed into a proton and an electron. Okay, with the latter being the electron is going to be ejected from the nucleus. Okay, so this is beta negative. Beta negative decay, right? Because we have a electron being emitted. Okay. Also in beta negative decay, so we have a neutron being changed into a proton and an electron. So what that looks like, so one neutron will be turned into one proton and an electron. Okay, we still have our mass and atomic numbers conserved, right? 1 plus negative 1 is 0, and 1 plus 0 is 1. Okay. Now, we also, or scientists noticed that antineutrino was also emitted here. Okay, so in beta negative decay, we have an electron and a antineutrino being emitted. Okay? And an antineutrino. Okay. So in beta positive decay, this is the emission of a positron. So this is kind of the opposite of an electron, right? Instead of it being -1, we have a charge of +1. So we call that a positron. Okay, so in beta positive decay, a proton is transformed into a neutron with a positron emitted. Okay, so a proton is transformed into a neutron and a positron. And we also have a neutrino will be emitted here. No line on the neutrino. Okay, a neutrino is emitted in beta positive decay. Yeah, so this is the same mass, but just the opposite charge of an electron. That is a positron. Okay? And here's an example, potassium dissociating into argon and a positron. Okay, we have our atomic and mass numbers being conserved here. All right, so we have beta negative where an electron is being emitted, and beta positive where we have a positron being emitted. Okay, so let's look at some beta negative decays. Okay, so remember beta negative decay, antineutrinos. Are being emitted. Okay, so radium-228. Radium from the periodic table has 88 protons, and it is undergoing beta negative decay. Okay, so I know it is going to be emitting an electron, and we need to make sure that our mass and atomic numbers are going to be balanced. So what minus 1 will equal 88? That is 89. And our mass numbers are going to stay, so we still have 228. And an element that has 89 protons is actinide, or actinium, sorry. And we're also going to have a antineutrino being emitted, okay, because this is beta negative decay. Okay, so yeah, let's continue. I would encourage you guys to pause this video and try to solve them on your own. Okay, so lead-212. Lead has 82 protons. Is dissociating through beta negative. So this next one will have 83. What has 83 protons is bismuth. And we are also going to have an antineutrino because this is beta negative decay. Okay, lastly we have cobalt-60. So cobalt has 27 protons. It is undergoing beta negative decay. So what minus 1 will give us 27, that'll be 28. We still have a mass number of 60. That's going to be nickel plus a neutrino, antineutrino, okay? So those are 3 examples of beta negative decay. And again, it's important that we are making sure that our mass and our atomic numbers are balanced here. And make sure we don't forget about our antineutrinos for beta negative decay. Oh. All right, so let's get into some beta positive decay. So, use an equation to determine and name the isotope produced in the beta positive decay of thallium-202. So thallium has 81 protons, has a mass number of 202. Thallium is undergoing beta positive decay, so we have a positive one there. And to make sure that is balanced, we need to have something that has 80 protons, mass number of 202, so that is mercury. And because this is beta positive decay, we're going to have a neutrino being emitted. Okay? So there is our beta positive decay equation. Now, how much energy will be released if the mass of the nucleus decreases by 0.001463 atomic mass units? Okay, so we know our change in mass is 0.001463 atomic mass units. Let's convert that to kilograms. Which will give us a value 2.42858 times 10 to the negative 30 kilograms. And we know from yesterday's class, change in energy is equal to change in mass times the speed of light squared. And if we multiply that by the speed of light squared, we get a change in energy equal to 2.186 times 10 to the negative 13 joules. Or if you want to put this into electron volts, you can divide that by 1.6 times 10 to the negative 19 joules per electron volt. And that will give you an energy release of 1.366 mega electron volts. Okay? I am totally fine if you leave your answer in joules. I actually prefer it in joules. It just means a little bit more to me. But if you want to convert it and present your answer in electron volts, that is totally fine. Just make sure you're able to go between joules and electron volts, right? All right. All right, so after further investigation, physicists came to the conclusion that the transformation or decay of a neutron involved a force called a weak nuclear force. Remember, we have four fundamental forces of the universe: electromagnetic forces, the weak force, the strong force, and the force of gravity, right? Physicists also came to the conclusion that beta decay involves antimatter. So antimatter is a form of matter that is similar to matter, but it has a key property, such as charge, which is opposite to that of ordinary matter. Okay, so today we talked about the electron, and the piece of antimatter for the electron anyways, is going to be the positron. Okay, so if an electron and a positron come into contact, they will annihilate one another, and it will result in a pair of high energy gamma rays traveling in opposite directions. Okay, if two electrons were to collide, momentum would be conserved, so the rate at which the electron and the positron are moving towards one another will be reflected in the amount or how energetic those photons are after they collide. Okay? So yeah, beta decay involves antimatter, so if an electron and a positron meet, so just to write like an equation for that. So an electron is -1 and 0, plus a positron, which is 1, 0. This will just form gamma rays. Okay? The last thing or another conclusion that physicists were able to reach after further investigation was that when electrons or beta negative particles are released, they are accompanied by antineutrinos or neutrinos, right? We talked about this. Remember, beta positive decay has neutrinos, and beta negative decay has antineutrinos. Okay, make sure we know the difference between those two. Okay, so we have neutrino in beta positive decay. And we have antineutrinos in beta negative. So what are neutrinos and antineutrinos? That's a really good question. So these are really, really, really small particles. They are neutral particles. And during beta decay, the kinetic energy of the emitted electrons were found to be of a lower kinetic energy than originally expected. And they were curious where that missing energy had gone, right? Energy cannot be created nor destroyed, just transformed from one form to another, right? So in 1930, this gentleman comes along, Wolfgang Pauli. He is also known for his Pauli exclusion principle, and that is involved with the spin up and spin down orientation of electrons in atomic orbitals. Okay, but Pauli suggested that the missing energy was being carried away by a tiny neutral entity which we call today is the neutrino. Okay, so neutrino is just kind of like the V, right? Antineutrino is the V with the line on top of it. Okay, so this explained the observations of missing energy of emitted electrons during radioactive decay. So neutrinos and antineutrinos have no charge and an exceedingly small mass. So they're really light and no charge, so they're kind of hard to detect. It was only recently determined that their mass was about 5.7 times 10 to the negative 37 kilograms. Right, this is tiny. It's 1.5 million times less the mass of an electron. Right, so really small, light, neutral particles, hard to detect and prove the existence of. So Wolfgang Pauli hypothesized in 1930 that these particles existed to account for the missing energy. And then about 26 years later, the existence of neutrinos and antineutrinos was confirmed scientifically by Clyde Cowan and Frederick Rains. Okay, so what we need to remember about neutrinos and antineutrinos, they're really light, they have no charge, and neutrinos are emitted in beta positive decay, and antineutrinos are emitted during beta negative. So remember, beta negative is when an electron is being emitted, and beta positive is when we have a positron. Being emitted. All right. So the Nobel Prize in 2015, for the physics anyways, recognized Takaki Kajita in Japan and Arthur MacDonald in Canada for their key contributions to the experiments which demonstrated that neutrinos change identities. Okay, so this metamorphosis requires that neutrinos have mass. And this discovery that neutrinos do have mass has changed our understanding of the innermost workings of matter and can prove crucial to our view of the universe. And this knowledge of neutrinos and subatomic particles have allowed scientists working on the Large Hadron Collider for multiple years to also acquire more information about the early stages of our universe, kind of shortly right after the Big Bang. Okay, so the last type of decay that we're going to talk about today is gamma decay. So gamma radiation or gamma decay, this is where we have a photon is emitted when a nucleon in a nucleus is in an excited state and then drops to a lower energy state. So this is similar to an electron making an energy level transition, kind of like what we saw in the last chapter, right? When we had something being excited from N1 to N6 in a hydrogen atom state, we need energy, right, to go to excite it from 1 to 6. We need energy. But when that excited nucleon goes back down, it's going to release energy in terms of a photon, right? So this is kind of similar to that. And how gamma decay looks, so for example, if we have a sample of, let's say, plutonium, and it doesn't really matter. I just had one on here, but I forgot what element it was. So Pu, plutonium, and this star up here indicates an excited state. Okay, and that is just going to emit a gamma ray, and we're still going to have plutonium because it's not emitting a proton or a neutron or anything like that. Plus a gamma ray. Okay, and it is no longer in an excited state after that. Okay, so gamma ray is the emission of a high energy photon from a nucleus. Okay, so next thing we'll talk about is the radioactive decay series. So often a radioactive nucleus will decay into a daughter nucleus, and this daughter nucleus is itself radioactive. So if it's radioactive, it is unstable. So it will decay again until it becomes stable. And that is the radioactive decay series. So if we look at lead-232 here, it undergoes beta negative decay. It turns into bismuth-212. Bismuth-212 is unstable, so it will undergo alpha decay and beta negative decay, forming thallium and polonium. Okay, and then thallium and polonium are themselves also radioactive. So polonium will undergo alpha decay, thallium will undergo beta negative decay, and then we are back with lead-208. Okay, and we would consider lead-208 to be a stable nucleus. So this chart here shows the radioactive decay series for uranium-238 to lead-206. So we start at uranium. It is losing mass number, so it's losing neutrons and protons. Right? It turns into thorium, which will then decay into protactinium, right, which will then decay into uranium, which again comes back to thorium, radium, radon, polonium, lead, bismuth, polonium, lead, bismuth, polonium, lead. Okay, so this, what we have down here is stable. And what do we mean by stable? Well, remember yesterday we talked about binding energies and binding energy per nucleon. So lead-206 will have a high binding energy per nucleon. So therefore, it will be a little bit more stable, right? So if it has a high binding energy per nucleon ratio, then it is more stable. All right? So this is a radioactive decay series. So I'm not expecting you guys to memorize the decay series for uranium-238, but I would expect you guys to be able to tell me what a decay series is. Okay, so that's all for today's lesson. So here is your assignment for today. I will post the solutions to the Google Classroom. So as always, if you need help or you have questions about anything, please don't hesitate to ask. All right, thanks for tuning in, and we'll see you soon.